If I stand right here, does it look like light is shining out of both of my ears? I just thought that was interesting. I've got a ball flying through the air. I threw it at 48 feet per second. It released from my hand at a height of 6 feet, and it's being pulled down by gravity. What's the height after 1 second? What's the height after 2 seconds? Well, that was easy enough, but now here comes the real question. Prove the maximum heights between 1 and 2 seconds. That's easy. Rolle's theorem. In fact, I'm not even going to use Rolle's theorem because it's just the mean value theorem for a certain situation. In each of these, I'll just say the mean value theorem, knowing technically this is Rolle's. You've got two heights that are exactly the same. I think this is a continuous path. I've never seen a ball start flying up, disappear for a second, and then reappear somewhere else. The ball continuously moves through the air. If it's at the same height twice, there must be some point in between where the tangent line slope is 0. Okay, physicists, I think what this means is if my position function tells me the height, then the derivative of that tells me the velocity. There'll be one point in the air where the velocity is 0. That, my friends, is the maximum height. There must be a point where the derivative equals 0 between those two because first note, it's continuous, and then secondly, it is differentiable. And with those two, the average rate of change between those two numbers is 0. There must be a point where the derivative is 0 somewhere in between them, at least one. But following the laws of physics, I'm guessing it's just one. Example 2. We've got a function up here. It's a quartic. If the mean value theorem can be applied, can you find all the points between -1 and 2 where the instantaneous rate of change, meaning the instantaneous slope, equals the average slope? I bet you can. Let's check it out first. Does the mean value theorem apply here? It is continuous. All polynomials are. It is differentiable. This is a smooth curve. I think we can use the mean value theorem here. Second, find that average rate of change. Boom! I found the actual points by plugging them into my function. Then I found the slope. So we have an average rate of change. Now we just need the instantaneous rate of change. And it turns out that the only point where my instantaneous rate of change, the derivative, is actually equal to my average rate of change is at the cube root of 5/4. I don't know that number. I imagine you don't either. But it's there. It's probably a little bigger than 1. So, quick review. If you want to use the mean value theorem, it must be continuous and differentiable on whatever interval you're given. If it's not, stop right there. Don't move on. Secondly, you have to make sure the average rate of change equals the instantaneous rate of change. They will equal each other at least once, at least one time. That's what the mean value theorem tells us.